Paul's transfer function. Transfer function of a continuous time system relates the Laplace transform of the continuous time output to that of the continuous time input.
Paul's transfer function relates the Z transform of the output at the sampling instance to that of the sampled input. Paul's transfer function can be of cascaded elements or closed-loop systems. The first one is cascaded elements. Here is a block diagram of a cascaded system. Here's how to derive the formula of a cascaded transfer function. S equals G S times X asterisk S as equation 1.1. Y equals H S times U asterisk S as equation 1.2. Taking starred Laplace transforms on both sides of the equation 1.1 and 1.2. The result is U asterisk S equals G asterisk S times X asterisk S as equation 1.3. Y asterisk S equals H asterisk S times U asterisk S as equation 1.4. Substitute U asterisk S from equation 1.3 to equation 1.4. The result would be Y asterisk S equals H asterisk S times U asterisk S equals H asterisk S times G asterisk S times X asterisk S as equation 1.5. Therefore, Y Z equals G C times H C times X C as equation 1.6. From the equation 1.6, divide both sides by X C. The result would be Y Z over X Z equals GH C. Therefore, Z times quantity GH S.
Here's another form of a cascaded system in its block diagram. Here's how you derive its formula. Use equals G's times X S as equation 1.7 and Y equals H's times U's as equation 1.8. Now substitute U's from equation 1.7 to equation 1.8, we get Y asterisk S equals H's times U's equals H's times G's times X asterisk S equals GH's times X asterisk S as equation 1.9. Therefore, Y asterisk S equals quantity GH's asterisk times X asterisk S as equation 1.10. Now convert Laplace to Z transform, we get YZ equals GHZXZ as equation 1.11. From the equation 1.11, divide both sides by XC, we get YZ over XC equals GHC equals C times quantity, GH's. Note: GZHC is not equals to GHC equals CGH's.
The second pulse transfer function is closed-loop systems. Here's an example of a closed-loop system block diagram. Here's how you derive a formula for a closed-loop system. S equals Rs minus Hs times Cs as equation 2.1. Cs equals Gs times E asterisk S as equation 2.2. Substitute Cs from equation 2.2 to equation 2.1. S equals Rs minus Hs times Gs times E asterisk S as equation 2.3. E asterisk S equals R asterisk S minus quantity G SHS asterisk times E asterisk S equals R asterisk S minus quantity GHs asterisk times E asterisk S as equation 2.4. E asterisk S equals R asterisk S over 1 plus GH asterisk S as equation 2.5. C asterisk S equals G asterisk S times E asterisk S as equation 2.6. Now substitute E asterisk S from equation 2.5 to equation 2.6, we get C S equals G asterisk S times R asterisk S over 1 plus GH asterisk S as equation 2.7. Then convert it into Z transform. The result would be C Z equals G Z times R Z over 1 plus GH Z as equation 2.8.
Digital controller. This can be easily obtained from its input-output characteristic, which is specified by means of difference equation. M, K, plus a sub 1 meter, K minus 1, plus a sub Nm, K minus N, equals B sub 0 E. K. plus b sub 1 e, k minus 1, plus b sub 0 e, k minus n, as equation 3.1, where m, k, equals output signal, e, k, equals input signal. Taking the z transform and simplifying equation 3.1, we get its pulse transfer function. G sub d, z, equals, m sub, z, over, e sub, z, equals, b sub 0 plus b sub 1 z power, negative 1, plus b sub 2 z power, negative 2, plus b sub n z power, negative n, all over, 1 plus a sub 1 z power, negative 1, plus a sub 2 z power, negative 2, plus a sub n z power, negative n. Closed-loop pulse transfer function of a digital control system. Here's the general block diagram of a digital control system and mathematical block diagram of a digital control system. Here's how you derive a formula for the closed-loop system. C's equals G's G sub D asterisk S times E asterisk S as equation 3.1. C asterisk S equals G asterisk S G sub D asterisk S times E asterisk S as equation 3.2. Converted into Z transform. C equals G Z G sub D Z E Z as equation 3.3. E Z equals R Z minus C as equation 3.4. Substitute E Z from equation 3.4 to equation 3.3. We get C equals G Z G sub D Z times quantity R Z minus C as equation 3.5. Transfer function is obtained from the equation 3.5, which is C Z over R C equals G sub D Z G Z all over 1 plus G sub D Z G Z.
Derivation of pulse transfer function. Using the equation above, we find that the sampled input, R asterisk t, to the system of figure, C, is R asterisk t equals summation of Rn tau delta t minus n tau as n goes from 0 to infinity, which is a sum of impulses. Since the impulse response of a system, G, S, is G, T, we can write the time output of G, S, as the sum of impulse responses generated by the input, equation 0.1. Thus, Ct equals summation of Rn tau gt, n tau as n goes from 0 to infinity. From the Z transform equation, Fz equals summation of Fk tau z power negative k as k goes from 0 to infinity, we will come up with Cz equals summation of Ck tau z power negative k as k goes from 0 to infinity. Using equation 0.3, with t equals kt, we obtain Ck tau equals summation of Rn tau gk tau minus n tau as n goes from 0 to infinity. Substitute equation 0.4 into 0.3 would result to Cz equals double summation Rn tau gk minus n tau z power negative k as n goes from 0 to infinity and k goes from 0 to infinity. Let m equals kn, we find Cz equals double summation Rn tau gm tau z power negative m plus n as n goes from 0 to infinity and m plus n goes from 0 to infinity, where the lower limit, m plus n, was changed to m. The reasoning is that m plus n equals 0 yields negative values of m for all n greater than 0. But, since g, m tau, equals 0 for all m less than 0, m is not less than 0. Alternately, g, t, equals 0 for t less than 0. Thus, n equals 0 in the first sum's lower limit. Using the definition of the Z transform, equation 0.6 becomes Cz equals summation gm tau z power negative m times summation of Rn tau z power negative n as n goes from 0 to infinity and m goes from 0 to infinity equals gzrz. This is a very important result, since it shows that the transform of the sampled output is the product of the transforms of the sampled input and the pulse transfer function of the system. Remember that although the output of the system is a continuous function, we had to make an assumption of a sampled output, phantom sampler, in order to arrive at the compact result of equation 0.7. Here are some example problems and solutions that we can practice to familiarize ourselves on the formulas and processes. Example number 1. Consider the closed-loop discrete data system shown in the figure. The output of the sampler is regarded as an input to the system. Thus, the system has inputs Rs and E**s. The signals E, S, and Y, S, are regarded as the outputs of the system. Here's how you solve this problem. Writing the cause and effect equations for E, S, and Y, S, using the gain formula, we get E, S, equals Rs minus G, S, H's E asterisk, S. Y, S, equals G's E asterisk, S. Notice that the right-hand side of the last two equations contains only the inputs Rs and E, S, and the transfer functions. Taking the pulse transform on both sides and solving for E, S, we get E asterisk, S, equals, R asterisk, S. Over, 1 plus, G, S, H's. Substituting E asterisk, S, we get, Y, S, equals, G's, times R asterisk, S, all over, 1 plus G, S, H, S. Taking the pulse transform on both sides of the previous equation and using the formula below, we arrive at the pulse transfer function of the closed-loop system, Y. S, over, R asterisk, S, equals, G. S, over, 1 plus quantity, G, S, H. S, asterisk. Taking the Z transform on both sides of the last equation, we have, Y, Z, over R, Z, equals, G, Z, over, 1 plus GH, Z. Here's another example. Example number 2. We show in this example that, although it is possible to define an input-output transfer function for the system, this may not be possible for all discrete data systems. Let us consider the system shown in figure below, which has a sampler in the feedback path. In this case, the outputs of the sampler Y, S, and Rs are the inputs of the system. Y, S, and E, S, are regarded as the outputs. Writing E, S, and Y, S, in terms of the inputs using the gain formula, we get, Y, S, equals G, S, times E, S. E, S, equals R, S, minus H's Y asterisk, S. Taking the pulse transform on both sides of the last two equations and after simple algebraic manipulations, the pulse transform of the output is written as, Y asterisk, S, equals quantity, G, S. R, S, asterisk, over, 1 plus quantity, G, S. H, S, asterisk. Note that the input R, S, and the transfer function G, S, are now combined as one function, G, S. R, S, asterisk, and we cannot define a transfer function in the form of Y asterisk, S, over R, S. The Z transform of the output is written as, Y, Z, equals, GR, Z, over, 1 plus GH, Z. This is an example of transfer function of zero-order hold problem. Consider that, for the system shown below, the sampling period is 1s. The Z transfer function of the system between the input and the output is determined using equation GZ equals 1 minus Z power negative 1 slash ZGPS over S. Thus, by executing the equation we get 0.426Z plus 0.361 all over Z squared minus 1.606Z plus 0.606. That's it. Hope you enjoy the video. Illustrations are on the description below. Thank you for watching.